Hello, in this video, the topics discussed will be about differentiation and integration. Differentiation and integration are both fundamental operations that are used to solve real-world problems. Differentiation focuses on calculating the rates of change and slopes of curves, while integration focuses on calculating areas and volume. Both concepts are often used in fields like physics, economics, engineering, and computer science. In today's video specifically, we will be exploring the core concepts of differentiation and integration, and then a real-world example question while incorporating some vector equations, and then the general differentiation and integration techniques to solve complex problems.
Differentiation involves finding the instantaneous rate of change of a function, measuring how a dependent variable changes with respect to an independent variable. Derivatives can be classified into different types based on their order. First-order derivative, denoted as f prime of x, represents the rate of change of the function fx with respect to x. In terms of geometry, it gives the gradient of the tangent line to the curve at any point. In physics, it describes a primary rate of change. Second-order derivative, denoted as f double prime of x, is the derivative of the first derivative. It is used to determine the nature of a point in a curve. If f double prime of x is greater than 0, the nature of the point is minimum and the graph is concave upward. But if it's less than 0, the nature of the point becomes maximum and the graph is concave downward. To precisely define a derivative, mathematicians use the concept of limit. The derivative is the limit of the average rate of change of the function as the interval becomes infinitely small. Over an interval of x plus delta x, the gradient is denoted by fx plus delta x minus fx over delta x, like how we use y2 minus y1 over x2 minus x1 to calculate gradient. As delta x approaches 0, gradient approaches exact value at x. This process relies on limits.
Okay, moving into derivative techniques, there are some techniques that can be used for differentiating an equation, starting from power rule. This technique just need to bring the exponent n down as a coefficient and subtract the original exponent by 1. The next one is constant rule. The derivative of the constant rule is always 0. Third one is constant multiple rule. When a differentiable function is multiplied by a constant, the derivative can be multiplied by the same constant. The next one is derivative sum. If a and b are differentiable functions, then their sum of two differentiable functions is the sum of their derivatives. More common derivative techniques is product rule, quotient rule, and chain rule. Actually, there are more differentiation techniques. This video covers ordinary differential equations.
Integration concept. What is integration? Integration is the reverse process of the derivative, also known as the antiderivative. Integration is useful in situations where we need to find the area under a graph, the volume of an object, or other quantities. The area under a graph is commonly used to find the cumulative sum of a function as the independent variable changes. The area under a graph, also known as the integral, can be approximated by calculating the Riemann sum as the number of subintervals approaches infinity. This is the first quadrant of x squared, between intervals a and b. If we want to find the area under the curve between intervals a and b, we can find the approximate value of the area by splitting the area under the graph into multiple subintervals. Therefore, we have split the graph into 4 subintervals, and so n equals to 4. The width of each rectangle can be calculated using the formula delta x equals b minus a over 2. Now we need to find the height of each individual rectangle, which can be done by evaluating fx at the start of each subinterval, also known as the left endpoint. The same thing can also be done at the end of each subinterval, also known as the right endpoint. Now we need to find the sum of the area of rectangles, given by these equations at the top. As you can see, the difference in space becomes smaller as n increases. The difference between the exact integral and the area calculated using the Riemann sum becomes more negligible as subintervals n approaches infinity. Therefore, as n approaches infinity, the Riemann sum approaches the exact integral of the graph between the interval a and b, given by this function below.
The next one is integration techniques. In the power rule, need to identify the exponent of a respected variable and add 1 into the exponent. Also, the equation needs to be divided by the new exponent. In the end, need to add the constant of the integration, that is c. The next one is constant rule. In this rule, just need to multiply the respective variables with the equation and add the constant of the integration. The next one is constant multiplication rule. This technique only needs to multiply the integration with the constant. Integration sum and substitution, product of sinus and cosinus, and the next one is integration product of tangents and secants is also some example of integration techniques. Another technique is partial function. This technique involves breaking a rational function into terms with a simpler denominator. By understanding basic integral technique, more complicated problems can be solved with more difficult techniques.
Engineers who work in the military section need to predict the trajectory of an artillery shell to calculate the effective range, maximum height, and time taken by the shell to reach the target. In an ideal case, air resistance and drag forces are ignored. The resulting trajectory is a perfect parabolic shape with constant value of g. In the real world, air resistance and drag affects the shell, causing it to not have a perfect parabolic shape. Instead, it has a skewed parabolic shape. If engineers can model the velocity vector equation of the gun, they can approximate the displacement and acceleration vectors. For example, after the engineers recorded the horizontal and vertical velocities of an experimental shell, they modeled this equation. To prove that these equations are correct, we can plot the displacement graph of the equation that we obtained using integration. First, we need to find the time taken for the projectile to impact the ground. When these values are plotted on a graph, we get this shape. This result is more accurate to the trajectory of a real-life artillery shell. And now that the displacement vector has been found, the engineers can calculate the position of the shell at any point in time.
In conclusion, both differentiation and integration techniques are important in solving real-world and theoretical problems. Differentiation focuses on rate of change with techniques like power rule, product rule, quotient rule, and chain rule, simplifying complex calculations. On the other hand, integration is the reverse process of differentiation. It is used to calculate areas under the curves, cumulative sums, and volumes. This can be calculated using power rule, constant multiplication rule, integration sum and substitution, and partial fraction. Applications such as the trajectory of artillery shells illustrate how both differentiation and integration provide insight into real-world phenomena like acceleration. Together, these concepts form a foundation for addressing complex challenges in fields like physics, engineering, and beyond. That's all for our presentation. Thank you.